Okay, welcome to Let's Get to the Marks, going through a GCSE Combined Science Chemistry Higher Paper 1. You've got a couple of weeks before the real exam, so let's get into it. Let's get working hard. This is the 2020 paper. There's 7 questions, hour and 15 minutes. What I recommend is that you grab a pencil right now, grab some old paper, pause the video at the start of each question, write down your answers. If you don't have pencil and paper, just do them in your head, then unpause the video and watch me go through the answers with the explanation. All right, let's get into it. Question 1. This question is about the extraction of aluminium. 1.1. An aluminium atom is represented as Al with a 27 above and a 13 below. Give the numbers of electrons and neutrons in the aluminium atom. So what we got to do here, folks, is know what these numbers are. Now, this top number is known as the atomic mass number, and that is the number of protons plus neutrons. So that equals 27. Now, the bottom number is the atomic number, but that is really the number of protons, and that never changes. So you've got 13 protons. And there's also a rule in chemistry, P is equal to E. So number of protons is equal to electrons. So some people say, can't I just think of this 13 as electrons? You can, but you get things called ions, where when atoms can lose or gain electrons. So their number of electrons, if they're an ion, will not be the same as this atomic number, but it will always be the same as the number of protons. Anywho, let's move on. So in this situation, it says give the number of electrons and neutrons in an atom of aluminium, or an aluminium atom. So the number of electrons, P is equal to E, is going to be 13 because the atomic number is 13. The number of neutrons is going to be 27 minus 13. And that means our answer is going to be 14 for the number of neutrons. And that will get you 2 marks and get you on the way. Don't forget to make some notes, have some revision cards with you when you're working through a paper. And if there's something you come across now in the last 2-3 weeks before your exams that you don't understand, make a note on a revision card and revise it a few times, and then you'll be all right when you come to your exam. All right, let's move on. Okay, aluminium is extracted by electrolysis of a molten mixture of aluminium oxide and cryolite. Figure 1 shows the cell used for electrolysis. Here's figure 1. We've got a metal wire, got a positive charge on it, and then we have a negative electrode down here. And these black rectangles, these represent the positive electrode. And then in the middle here, this gray liquid is the molten, which means melted, mixture of aluminium oxide and cryolite. And then we have molten aluminium at the bottom. Aluminium is produced by the reduction of aluminium oxide, Al2O3. What is meant by the term reduction? There's oil rig, you've probably all heard of that. And that stands for oxidation. Oxidation is loss of electrons. I can't be bothered to write the word electrons, so I'm just doing E minus. And then reduction is gain of electrons. Now, that is one way of remembering oxidation and reduction. So we could say reduction is gain of electrons. But there's also another thing that reduction is. The original meaning, when they first came up with the word reduction in chemistry, reduction is loss of oxygen, or is the removal of oxygen. What they found out later on, that when oxygen is removed, you're actually gaining electrons. So reduction is the removal of, so then they changed it to reduction is gain. So either of those will do you good. I would go with the first one because it fits with oil rig. Oh my gosh! 1.3, oxygen is formed at the positive carbon electrodes. Explain why the positive carbon electrodes must continually be replaced, and that is 3 marks. So I'm going to go up here, guys. Okay, it tells us that oxygen is produced at these 3 positive electrodes. So let's imagine oxygen is coming off, right? Guess what these electrodes are made of? They're made of an inert material. That means an inner graphite electrodes. The graphite doesn't react with anything there. The problem is graphite is actually an allotrope of carbon. So graphite is made of carbon atoms. As the oxygen forms, it reacts with the carbon atoms in this reaction. So the oxygen getting produced at the positive electrode is reacting with these carbon atoms that are in this black rectangle in that electrode to make carbon dioxide. So actually our solid electrodes are slowly wearing away as the oxygen gas reacts with the solid carbon to form carbon dioxide. And so we just need to smash all that down in the question and pick ourselves up 3 marks. So what we're going to do here, we're going to say the electrodes are made of carbon. Actually, they told us that in the question, which was nice of them. So the electrodes are made of carbon. It reacts with, oh my days, with the oxygen. There's our first mark, reacts with the oxygen to form carbon dioxide, which is a gas and so escapes. And of course, gases have mass. So what we're really saying is the gas goes away, carrying that carbon away, reacts with the oxygen, carbon dioxide, forms carbon dioxide, which is a gas, and so escapes. Now, if you want, you could do the equation to show you understand that, and you can probably get all of the marks from the equation. And this is why they are eroded, because the solid electrode is becoming a gas. And so your marks are for reacts with oxygen, forms carbon dioxide, and then the third mark is carbon dioxide is a gas. Look, I'll put 4 ticks because I'm a wally. All right, let's move on. 1.4, a substance conducts electricity because of free moving charge particles. What are free moving charge particles in a carbon electrode made from graphite, molten mixture of aluminium oxide and cryolite, and a metal wire? So we've got 3 different moving charge particles. So in graphite, okay, I'm just going to show you. Graphite is a giant covalent structure. You need to learn this structure, by the way, if you don't know it. Each carbon atom is bonded to 3 other carbon atoms, okay? And that means that carbon's in group 4. It means there's a free electron hanging about for each one of these carbon atoms. It's arranged in layers, and those electrons can carry charge throughout the graphite structure. Now, they are called delocalized electrons. That's what carries the charge in graphite. So what are the free moving charge particles? They're delocalized electrons, and that's going to get you big fat mark. What about in a mixture of aluminium oxide and cryolite? Well, if you check out aluminium oxide, Al2O3, when you melt it so it goes from S solid to liquid, it forms ions, and these are free moving ions, and it forms aluminium ions and oxygen ions that can carry charge because they're free to move. So we're going to say free moving ions, or we can just say ions, and the mark scheme will give it a mark for ions. Aluminium and oxygen ions, Al3 plus or O2 minus, or you can just say that. Now, in a metal wire, what are the free moving charged particles? Well, a metal wire, metals are arranged in this structure. You've probably seen it before. It's a regular structure with rows of metal atoms together. Now, are they atoms? No, because what they do is they lose their outer electron, leaving behind positive ions like this. We draw a little circle with a plus. So they're not actually atoms, they're metal ions. But these aren't free to move. But what is free to move? The electron that they've lost can move anywhere it wants through that structure and carry charge. So guess what? We call these the same as in graphite. These are delocalized electrons. And so we get another fat mark for that. And there we go. That's the end of question 1. How did you do? Okay, give yourself a pat on the back. Let's move on. Don't forget to pause the video at the start of each question. Let's go. Question 2. This question is about substances with covalent bonding. Figure 2 shows a ball and stick model of the water molecule H2O. Here we've got figure 2 suggests one limitation of using a ball and stick model for a water molecule. So if we use this ball and stick, what doesn't it really show? It doesn't really show what the bonding is. It doesn't show that they're 3-dimensional. What else doesn't it show? Let's have a little think. If you're thinking about real atoms, it doesn't show any electrons. It doesn't show the type of the bond. No electron shells. So I'm going to say does not show electrons or shells of the atoms. So I can't tell how many electrons are in the hydrogen or the oxygen? What else can't I tell from it? It is not 3D, okay? It's not really a three-dimensional model, and it doesn't show the correct size of the atoms. It does not show the scale of the atoms. But what do I mean by that? Well, just to give you an idea, you might say to me, yeah, but sir, doesn't it show that hydrogen is smaller than oxygen? It does, but hydrogen has a mass of 1, right? Oxygen has a mass of 16. So in theory, if we wanted to accurately show this, oxygen is a lot bigger than hydrogen, right? Because its mass is 16 times more than that of hydrogen, which isn't very easy to show in a model. Anywho, any limitation about this model is good. So the fact there's no bonding electrons, the fact there's no shells, the fact that it's not three-dimensional. Right, ice has a low melting point. Water molecules in ice are held together by intermolecular forces. Complete the sentence. Ice has a low melting point because the intermolecular forces are, if you've got a low melting point, what are they? Are they strong or are they weak? Intermolecular forces are always weak, people. So you can have stronger weak intermolecular forces, but generally they're always weaker than bonds. So, and what are we talking about? Just in case you don't know, I'm not going to be a little bit overboard and I over explain things, but here's a water molecule and here's another water molecule. So the reason why ice has a low melting point is because if it was this is a simple covalent molecule. If it was a giant covalent molecule, that's what would happen. It would have bonds like this. If it was like diamond or graphite, it would have solid black covalent bonds. We draw them as black lines. They're not really black, but it would have solid covalent bonds between the different molecules. It doesn't. Instead, between these different these bonds are really strong, by the way. They're covalent bonds. Never say that that the water has weak bonds. It doesn't. It's got very strong bonds. But what's holding one water molecule to another, we use a dashed line, is weak intermolecular forces. And these weak intermolecular forces are what are easy to break and what gives water a low melting point. And anything else that has a low melting point has weak intermolecular forces. Okay, 2.3 shows the structure of a molecule. We've got oxygen atom, we've got hydrogen atom, we've got carbon atom. What's the molecular formula of the molecule? So what I want to do, right, I'm going to start with a carbon atom. Where are we going to go next? Hydrogen, there's 4 of them, CH4, and I think that is just one oxygen. There you go, CH4O. There we go. The molecular formula shows each element and the number of atoms of each element. Okay, great. That's going to get us a mark. Let's move on. Don't forget to pause the video, have a go, and then unpause and watch the explanation. 2.4, diamond has a giant covalent structure. What is the number of bonds formed of each carbon atom in diamond? So diamond has a giant covalent structure. Check out my uber bad drawing of diamond. So diamond, each carbon atom is actually bonded to 4 others, which is a little bit hard to draw, to be honest. But each carbon atom is bonded to 1, 2, 3, 4 others. It's in group 4, and the group number is the total number of bonds that carbon can have is 4. Give 2 physical properties of diamond. Right, look at all those bonds that are hard to break. So we're going to go with high melting point. Obviously, unlike water, it doesn't have any weak intermolecular forces. It's just got lots of strong covalent bonds that you need to break. Also, very hard. It's hard, or we could say it's solid at room temperature. One of the hardest substances, naturally occurring substances on the Earth. 2.6, name 2 other substances with giant covalent structures. Well, we just talked about one, graphite, which is also made of carbon, but the only difference is it's arranged in layers. And each carbon only has 3 bonds. So graphite is another giant covalent structure. And we can go for silicon dioxide. Silicon dioxide. And you actually have to know these ones are on your specification. So you need to know 3 giant covalent structures: diamond, graphite, silicon dioxide. If you didn't get it right, what are you doing just sitting there? Grab a little revision card, write down, name the 3 giant covalent structures: graphite, silicon dioxide, diamond, pin them up somewhere, put them up somewhere, make sure you revise it before the exam in a few weeks. Okay. Question 3. Some students investigated the thermal decomposition of metal carbonates. The word equation for the reaction is metal carbonate goes to metal oxide plus carbon dioxide. The students made the following hypothesis. When heated, the same mass of any metal carbonate produces the same mass of carbon dioxide. The students heated a test tube containing, what was it containing? Copper carbonate. Table 1 shows their results. So time the test tube containing copper carbonate was heated in minutes 0, 17.7 grams, was the mass of the test tube and contents. After 2 minutes, it went down to 17.1. After 4 minutes, it's still gone down. 6 minutes, it hasn't gone down anymore. Okay, let's move down. Plan a method students could use to test their hypothesis. You should show how the students use their results to test the hypothesis. You do not need to write any safety precautions. So we don't need to say wear goggles, heat-proof mat, any of that business at all. So let's get into it. Exactly how would you carry out this experiment? So let's go back up and have a little look. They want to do what was their hypothesis? When heated, the same mass of any metal. So what they need to do is heat 5 different metal carbonates, and they need to do the same thing they're doing here, which is measuring, weighing it until it gets to a constant mass. Look, and then no more gas is coming off, and then we can see how we're doing. So what we're going to keep the same. So I'm going to say using 5 different metal carbonates. What do we want to do? Weigh, test tube and carbonate together. First of all, use same mass of metal carbonate for each experiment. Then I want to say weigh the test tube and the carbonate together. We're then going to heat heat for 5 minutes, then cool and re-weigh. Keep doing this until the mass does not change. Now, why do we do that? Because when the mass does not change anymore, the reaction is done. No more carbon dioxide's coming off. All of the carbonate has broken down from metal carbonate into metal oxide and carbon dioxide. And we know that because heating it doesn't release any more carbon dioxide. So we're going to keep heating it until the mass does not change. We call this heating, not heating until a constant mass. So that's what we call that. So what I'm talking about is you take your metal carbonate, right? And I'll give you an example. So you got a metal carbonate like that. Oh my days, that's some bad writing. And when you heat it, it's called thermal decomposition, because you need to make a note of that if you don't know what thermal decomposition is, because it breaks down into a metal oxide and carbon dioxide. So once there's no more carbon dioxide coming off, then the weight will not go down anymore, because the carbon dioxide's a gas and it escapes the test tube. So and once the weight doesn't go down anymore, there's no metal carbonate left. It's all turned into metal oxide and carbon dioxide. And so the experiment's done. So we then need to say calculate how much carbon dioxide's been released. So carbon dioxide has been released. How would you do that? Well, you'd take the mass from before and then subtract the final mass, and then you'd say, so I might want to say how I do that. Take weight of, it should say mass, weight of test tube and carbonate before minus test tube and oxide after. So that's how you're going to find that out. That's the calculation you're going to do. And then you just want to say maybe repeat 3 times for each metal carbonate, finding the average mass of CO2 released for each metal carbonate. There we go. And we just got to make sure, yeah, that's it. That's it. That's it. Should get you all of the marks. What's going on here? I'm doing a little funny dance. Ding, 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 ding. Um, and there we go. That's going to get you to 6 marks. So use 5 different carbonates, use the same metal for each experiment, same mass, I mean. Start with like 10 grams of each. Weigh the test tube and carbonate together because each test tube might be weighing slightly different. They're not all identical. Heat for 5 minutes, then cool, reweigh. Keep doing this until the mass doesn't change. So telling them to heat and then do it till a constant weight. Calculate how much carbon dioxide has been released. How do we do that? Well, we take the weight of the test tube and carbonate before, and then we weigh the test tube and the oxide after you've reached constant weight. So that's explained how to do that. And then I'd say repeat 3 times for each, finding the average mass. I could have put look for anomalies, compare the results, and take away anomalies if I want to get funky. And then there we go. That's 6 lovely marks. All right, let's move on. This question is about acids, alkalis, and bases. A student reacted zinc oxide powder with hydrochloric acid to produce zinc chloride solution. 4.1, complete the equation for the reaction by writing the state symbols. 2 marks. So we've got zinc oxide. Now, guess what? They give you clues in the question for these ones. So read it carefully. Questions about acids, alkalis, and bases. A student reacted, zinc oxide powder. Well, a powder is going to be a solid, right? With hydrochloric acid. Every single acid is AQ. With zinc chloride solution, what does solution mean? That means AQ2. So let's get down and put these in. So we know that's a solid, told us there, powder. Hydrochloric acid, you just have to know off by heart. Acids are all aqueous, so if you don't know that, make a note. Zinc chloride, it told us it's a solution because you can get zinc chloride solid, but obviously it's in the water that was with the acid, so it's aqueous. And then water, you can't have aqueous water. Water is known as a liquid because AQ means dissolved in water. So water is just a liquid unless it says steam or ice in the question. And there we go, 2 beautiful marks. Give one way that the student could speed up the reaction between zinc oxide powder and hydrochloric acid. So come on, this is kind of a paper 2 question almost, but how do you speed up reactions? Well, we could say increase the temperature by heating. So if you use heat, you're going to speed it up. We could also say use a catalyst. We could also say increase the surface area. You can't really increase the surface area of the zinc oxide powder. It's already got the largest surface area it can have. We could say increase the concentration of the acid. That's definitely one we could say. All right, let's move on. Okay, hydrochloric acid was the limiting reactant. How could the student know when all the hydrochloric acid had reacted? Let's look back at the equation. So we've got zinc, we got solution, we got aqueous. Once all the hydrochloric acid has reacted, check this out. I'm going to put a state symbol. Hey, hey. Okay, if I keep adding zinc oxide, what's going to happen when there's no more acid? I'm just going to have salt, water, and zinc oxide. The zinc oxide is going to float in the water, and yeah, it's just going to float there in the water and the solution. So that's how we'll know. We add the zinc oxide to excess, and then we will see the solid. So we will say ZNO, or zinc oxide, will be seen floating, will no longer disappear. Okay, so something along those lines, you'll see some excess zinc oxide. How could the student obtain zinc chloride solution from the reaction mixture when all the acid was reacted? So if we want to get zinc chloride solution from the reaction mixture, now they're not saying zinc chloride, they're saying how do we get that aqueous solution of water and zinc? So what we're going to have to do, we're going to filter. Now I know some of you will say evaporate the water and you'll have mashed that one up, but that's just life. Don't overstress. So we're going to filter, and that will give us the zinc chloride solution. So the answer here, folks, is filtration. And hopefully, when you see the next question, you'll have gone back and corrected this if you'd written the wrong thing. So Describe how zinc chloride crystals are produced from the zinc chloride solution. So maybe now, if you'd written evaporate up there, you'd realize, hold on a minute, how do I get crystals from a solution? Oh, evaporate. Can't be the same thing twice. So what's happening is you've got zinc chloride and it's aqueous. Okay, zinc chloride solution. They want to get the water away and just leave behind solid zinc chloride. So what we want to do is we want to heat gently with electric heater. Best not to use a Bunsen burner, but you can use a Bunsen burner as long as you use the word gently. Heat gently with a Bunsen burner. We can just say heat with electric heat. That's going to evaporate some of the water. Now, it's better to then say leave somewhere cool for crystallization. Okay, so key words here, guys. Whenever you're talking about evaporating the water, it's best to actually just evaporate some of the water until you see crystals and then leave the rest to evaporate by crystallization, which you can do in a cool area. There's a reason for that. When you're heating things violently or boiling things or bubbling away and trying to evaporate all the water, some of your solid zinc chloride might spit out of the beaker and you might actually lose some if you're overheating it. So it's best to use crystallization, which is a more gentle process for getting rid of all the water. All right, let's zing down. Sulfuric acid and sodium hydroxide react to produce sodium sulfate. So that's an acid and a base reacting to form a salt. Sulfuric acid is gradually added to the sodium hydroxide solution. The pH of the mixture changes as the sulfuric acid is added until, this is going to be key, this is why we highlight, until in excess. Acid in excess. Suggest the pH at the start before the acid is added and then when the acid is in excess. So we want the pH at the start. Sulfuric acid is added to sodium hydroxide. Sodium hydroxide is a base, so pick any strong base pH. So pH at the start, I'm going to go pH 12, but you could say 13, you could say 14. Okay, sodium hydroxide is a strong alkali or base, so it has a high pH. At the end, we're adding sulfuric acid, which is a strong acid. So I would suggest anything like pH 1 or 2. Once the acid's in excess, it means it's gone past neutralization. So I'm going to pick like 1. I'm going to say pH 1, but you could say 2. You'd probably say 3. Anywho, bish bash. There we go. Right. Complete this symbol equation for the preparation of sodium sulfate. You should balance the equation. So we've got sodium hydroxide here. That's a metal base. We've got sulfuric acid. We're going to make sodium sulfate. This is a very hard equation, actually. So when we look at sodium sulfate, writing the formula of sodium sulfate, a lot of you guys are going to write this, and this is wrong. Okay, that is incorrect. It's a nice try, but no cigar. What you got to do, sulfuric acid, or sorry, sulfate ions. You have to know this off by heart. So if you don't know it, grab a revision card, make a note. Sulfate ions have the ionic charge of 2 minus. So SO4, 2 minus. So when they join with sodium, which is a group 1 metal, so forms a +1 ion, they're not going to get together NaSO4 because this will not satisfy the sulfate ion. The sulfate ion is going to be like, I'm still negative. You need to make me more positive, bro. So along comes another sodium ion, and 2 pluses cancel out the 2 minus because you get 2 plus, 2 minus. So the formula for sodium sulfate is Na2SO4. Now, do you need to show the 2 minus? No, it's been cancelled out by those 2 sodiums. But that's the way you work out the formula, or you have to know those different ions, including carbonate, which is CO3 2 minus. So here are the other ions you need to know off by heart. If you don't know, get to know, right? Nitrate is NO3 minus. So you need to know these charges off by heart. And of course, chloride ions are minus. They often come up in salts as well. So learn them off by heart, peeps. Hydroxide ions, here's another one, OH minus. So learn them off by heart. Those ions you need to know off by heart for your exam. So if you don't know them, get to know them. They're going to help you out in weird little ways like this. Okay, what do we make when we do base plus acid? We make salt and water. So now I just need to put the water there, sodium sulfate plus water. I need to balance. So I've got a 2 there. I need a big fat 2 there. Let's just check this balance is 2 sodiums, 2 sodiums. 2 H's and 2 O's. Okay, I got two H's there. I got an O. No. I got to balance this up, folks. Um, oh my good gosh. Do I even need that there? Yeah, I need a two there, baby. So four hydrogen, I need a two here. Okay, two times H2, there's H2 there, there's two times H there, that's four H's. I've got two single O's there, and I got two times O there. We're balanced, peeps, we're balanced. Okay, I needed a two in front of the H2O, I needed a two there, bish, bash, bosh. Right, wowza, I had issues. Let's move on. Right, 4.8. A solution of hydrochloric acid had a hydrogen ion concentration of 1 mole per decimeter. Water was added to the hydrochloric acid until the pH increased by 1. So that means it went from like whatever the pH was, pH 3, it went up, increased to pH 4 by adding water. Okay. What was the hydrogen ion concentration of the hydrochloric acid after the water had been added? So it's 1 mole, 1 mole. Bum, bum, ba, ba, da, ba, dum, bum. Well, it's got weaker, and it's got weaker by a factor of 10. So if we were 1 mole and you get weaker by a factor of 10, you're going to go down to 0.1. So the way pH works, just to show you guys, right, you can have pH 1, 2, 3, 4. Okay. As you go down in pH, you want to divide by 10 each time is what happens to the hydrogen ion constant. You're getting less hydrogen ions. Hydrogen ions are what makes something acidic. It's the H plus ion that makes things an acid. Notice hydrochloric acid, H2SO4, HNO3. All acids have hydrogen ions. So the more hydrogen ions you have, the more strong you are. As we decrease, we decrease by a factor of 10. So if I go from pH 1 to pH 3, I've divided by 100. This was just one pH from 3 to 4. So we just divide by 10. So 1 divided by 10 is 0.1. If we were going the other way and you got an alternative question and it said you had something with pH 4 and it went to pH 2, how many times stronger is it? Well, it'll be 100 times stronger because you go 10 times 10. If they said something went from pH 4 to pH 1, it'd be 1,000 times stronger because you go 10 times 10 times 10. Anywho, let's move on. Right, we're on question 5. A student investigated the temperature change when magnesium was added to copper sulfate solution. This is the method used. Pour 30 centimeter cubed of copper sulfate solution in a polystyrene cup. Measure the temperature of the copper sulfate solution every minute for 3 minutes. So they've put the solution in there. Then they've measured the temperature for 3 minutes. Add magnesium on the 4th minute. So on the 4th min, I like to do little things so it helps me understand. So on the 4th minute, they've added magnesium. Measure the temperature of the mixture at 5 minutes. So 1 more minute, and then every minute up to 14 minutes. What is the dependent variable? What are they measuring in this investigation? Well, they've said it a number of times. Measure the temperature of the solution every 3 minutes. So they're measuring the temperature. The temperature. Okay, so of the solution, I shouldn't just write temperature. I should write of the solution in case the examiner punches me in the face and doesn't give me the marks. Okay, this is quite difficult. So this is a really good one for you to have experienced before your exam, whether you're doing combined science or not combined science. This is a very important graph, okay? Very difficult, very high level. This is level 8, 9, this graph. So if you get confused by it or you're baffed, don't worry. Here's the students' results. So first of all, these are the results before they mixed the chemicals together, and then afterwards, temperature went up and then started going down. And then what we're going to do here, folks, is go down. Suggest why the copper sulfate solution was left for 4 minutes before adding the magnesium. So this is copper sulfate was left for 4 minutes before to establish the initial temperature. So the initial temperature stabilized basically to get a constant initial temperature. Complete figure 4 by drawing a line of best fit through all the points after 7 minutes, extending the line back to 4 minutes, and that is 2 marks. The temperature change for the reaction is the temperature difference between the two graph lines at 4 minutes. Determine the temperature change for the reaction, another 2 marks. This is a really key skill. And also it's a very difficult skill. So don't worry if you flop on this, but why don't you, when I go back up to the graph, pause the video and have a go. So first of all, just go through in your head what you do. You're drawing a line of best fit through the points after 7 minutes. So on the right hand side of the graph, you want to extend the line going back till it reaches 4 minutes. The temperature change for the reaction is the temperature difference between the two graph lines at 4 minutes. Determine the temperature change for the reaction. So I'm going to go up here and I'm going to make this a little bit bigger. Oh, days. Now what you've got to do, they're asking you to do a line of best fit here and extend it all the way back to 4 minutes. And then they want you to determine a temperature change. So why don't you go ahead and have a go at that, and then unpause the video and I'll explain how to do it. This is a difficult skill, but one that you do need to know. So let's smash through it. Okay, here we go. So some people may have done this and they may be like, oh man, it's kind of a curve in it. So I got to do that, right? Now you may have done that. That's not correct. So what you do with these ones, you're going to put a straight line through, and I'm going to actually extend it all the way to that end. And I'm going to extend this going through here, and I'm going to do it up to the 4 minute line. Now this is the 4 minute line. Look. So I want these lines to intersect. Okay. And now the temperature change, this was the initial temperature. So what was my initial temperature? That is 17.2.4, 17.6.8, 18. So this line is right bang in between 17.4 and 6. So that is 17.5 degrees. By the way, that line, extending that line back, intersecting the 4 minute area, you don't have to have drawn this black vertical line, but I did just to make it clear. That is worth 2 marks. Now this calculating the temperature change is also going to be worth 2 marks. So what we're going to do now is we're going to draw a line across here. I'm going to do that in a different color for you. So I'm going to draw that. That's where the lines intersect. And that is going to be 26.4. Okay. Show the examiner you're trying by drawing on the graph. You'll often, if you've flopped everything else, you'll pick up a mark for that. So 16.4, I make that. That is the point where the two lines intersect. So now my temperature change is 26 point. I said 16.4 because I'm dumb. Right, 16.4 minus 17.5. That is going to give me. Where's my calculator? Smash that out, please, Bob. That is going to give me. Now there will be some variation because. Different people might say, look at where it intersects. It like I could have drawn that line a bit lower. So I make that 8.9, but look, it all depends on how, look, my line is kind of not going through the center of these X's. So in a way, you know, I could have done that. Whee! And then that is going to change my answer completely. So let me just show you. If I do that, bash there, she's probably more accurate. I think both will be on the mark scheme. Then my line is bang smack in the middle. That's 26.2, 26.3. So it might actually be that this is 20. I think this is probably more accurate, 26.3. I've had to change my line of best fit to make it go through the crosses, the points a little bit more accurately. And then if I do 26.3 minus 17.5, I get 8.8. So it depends. They both should be on the mark scheme because there's a little bit of variation in how people draw the lines and how they read that off, and they're going to allow that. So there we go. I think 8.9 or 8.8. 8.8 is probably my better answer, but that is going to get you 2 marks for working out the temperature change, 2 marks for doing that line, 4 lovely marks. Difficult question. That is actually something that you will do in A-level chemistry if you are an A-level chemist. Okay, 5.5. Explain why the temperature of the mixture decreases after 7 minutes. So after 7 minutes, so at first the temperature of the mixture goes up, then after 7 minutes it starts decreasing. Why is that? Well, the reaction's over, so it's not releasing any more heat because the reaction's done. And secondly, what happens to the heat that's in there? It goes out to the environment around. So what we want to say is the reaction is finished. The reaction is complete. It is exothermic, and so after it finishes, it is no longer releasing heat. Also, the heat is being lost to the surroundings or the environment or the atmosphere. So essentially, although it went from 17.5 up to like 26 degrees, that heat that was released into the solution and the beaker is now leaking out into the air. And so that's what we're trying to explain. The reaction's done, so no more heat is coming from the chemicals. And the environment, the solution, the glass, the air, the heat is starting to spread and dissipate through that environment. Okay, let's zing down to 7.6, 5.6. I'm going a bit loopy. The student repeated the experiment with an unknown metal Q instead of magnesium. All the other variables were kept the same. The student recorded a smaller temperature change. Suggest the identity of metal Q. Give a reason for your answer. So, do they give us any other metals in this question? Suggest why copper sulfate solution was left for 4 minutes. So if it has a smaller temperature change, it means it is less reactive. So pick any metal that is less reactive than magnesium. So you can pick any metal that's less reactive. I'm going to go with zinc. So if you know your reactivity series off by heart, if you don't, you might want to have a brief look at it. You don't have to know it perfectly, but just have a good idea of it. So I'm going to go with zinc. It is less reactive than magnesium. Magnesium's pretty high up, so they're giving you quite a range of things you could say. You could have said iron, etc. So yeah, zinc, and because it's less reactive. But you could say really any less reactive metal. Difficult one. We've got copper sulfate solution contain 0.1 moles of copper sulfate dissolved in 0.5 decimeters of water. Calculate the mass of copper sulfate in 30 centimeter cubed of this solution. Relative formula mass is CuSO4 equals 159.5. So I understand this one is a hard one. That's why it's worth 4 marks, this calculation. They want the mass in G. They've given us moles. I always like to identify what my numbers are. They've given me volume. They've given me another volume there. And they've given me MR. Well, first off, bust out your triangles. So you have to know this off by heart. Mass over MR times moles, right? You've got to know that off by heart. There's a second triangle in chemistry for combined science you've got to know off by heart, and it's mass over concentration times volume. So I'm going to start over here. Why? Because I've got MR right there, and I've got N right there. So I'm going to do 159.5, which is the MR, and I'm going to times it by N to get myself the mass. And this is going to pick you up maybe 2 of the marks. So 159.5 times 0.1. So 159.5 times 0.1. And we've got 15.95 grams. Now, that's the mass we've got. What is the mass in? It's in 500 decimeters of water. Now, this is a volume and this is a volume, but what do you notice that's different? That's centimeter cubed and that's decimeters. I want to put these both in the same. You can either divide that by 1,030 or you can times that by 1,000. I'm going to times the 0.5 by 1,000. So basically, I've got 15.95 in 500 centimeter cubed. What is the mass going to be in 30 centimeter cubed? That's what we're asking ourselves. So if I know that I have 15.95 in that, what is the mass in that? So I could just go 30 divided by 500 times 15.95. That's one of the ways I can do it. You could work out, oh, I'm going to work out how many grams per centimeter. So I could do instead, another way is 15.95 divided by 500. That works out how many gram per centimeter, and then times by 30. That's another way to do it. So we could do that. Divide, I'm going to do that way. Divide by 500 equals that, times 30 equals, I got 0.957 grams. So we could do it like that as well. Okay, that is 4 fat marks. There's a number of ways to do this, but it wasn't exactly easy. Question 6. So what do we have here? We have question 6. This question is about gold and compounds of gold. In the alpha scattering experiment, alpha particles are fired at gold foil. Alpha particles are positively charged. Figure 5 shows the results. Alpha particle being pew, bang. Most alpha particles are not deflected, so most of them go through. Look at that thick black line. Most of the alpha is going through. Some is going off course, and some is deflecting and deflecting on that side. What two conclusions can be made from the results? Conclusions are facts. What two factual things can we say about these results? Tick 2 boxes. So some of these are going to be things we know, but they're not fact from these results. Atoms are balls of positive charge with embedded electrons. Can you tell that from the results? No, you can't tell that from the results. Atoms are tiny spheres that cannot be divided. We can't tell that from the results. Atoms have a positively charged nucleus. Maybe because these things are deflecting, so they're hitting something small and hard, and probably positive because they're bouncing off and they're positive, and positive repel. Mass is concentrated in the nucleus, the center of atoms. Neutrons exist within it. Well, we can't tell that, so it's going to be these two. You can't tell that there's neutrons in there. There's nothing here that tells us that. Okay. I actually think this paper is quite hard, which is why you've got to do all the papers before your exam. 6.2, the gold foil is 4 times 10 to the minus 7 meters thick, 2,400 atoms thick. What is the diameter of one gold atom in meters? Give your answer to 3 sig. Well, if we know that that's the thickness and that's how many atoms, we want to do 4 times 10 to the minus 7. And we want to divide it by the number of atoms. And that is going to give us the thickness of one atom. So let's go ahead and smash that in the old calculator. So if I do 4 times 10 to the minus 7 and then divide by 2,400, I'm going to get 1.67 times 10 to the minus 10. So 1 point, if I round it, 67 times 10 to the minus, was that 10? Yeah, minus 10. Now give it to 3 significant figures. So I've kind of cheated there by putting the answer like that. What you're going to get in your calculator is like this. And so I'm just saying, look, the 6 here is bigger than 4 or 5. So you're going to round that up, push that up to 7, and they're the ones we want to show. So 1.67 times 10 to the minus 10. Make sure you know how to put in the minus 10 on your calculator. So you should just have to press 4, and then there's a times 10 button, and then you just write minus 7. So you just put times 10, and then you just put minus 7. Okay, make sure you know how to do that. Otherwise, you're going to lose marks in your GCSE. All right. Going through 6.3, gold reacts with the elements in group 7 of the periodic table. 0.175 grams of gold reacts with chlorine. The equation for the reaction is 2Au, which is gold, plus 3Cl2, diatomic chlorine, goes to 2AuCl3. Calculate the mass of chlorine needed to react with 0.175 grams of gold. Give your answer in milligrams. Relative atomic masses. Boom, boom, boom. Let's identify. Let's find out what we're doing, folks. Right, first of all, identify. So, data, that is mass. And this is going to show you the equation. Look, I've got a ratio. You just know this stuff is going to come in, right? When they give you the equation, it's not for any other reason than that you need that. Okay, so we've been given the mass. We're asked to find the mass of chlorine, and we've been given the MR. So peeps, you know the coup. You have to know this one off by heart. If you don't know it, slap yourself in the face and learn this one off by heart. Mr. Moles or whatever, mass equals Mr. Moles. Just mass over mr times moles. I always write n for moles, by the way, number of moles. Okay, so Now we know what equation we're bussing. They're asking us to find out about the chlorine. So what's the other thing? So find the mass of chlorine. What have they told us? 0.175 grams of gold. So we know that. Calculate the mass of chlorine needed to react with that. So we know the AU, we know the gold. Let's find the moles of gold to start with. 0.75. Right. So we want to do mass over MR. So 0.175. That's grams. Leave the unit in, peoples, so you don't get confused. And then write the AU. AU is 197. Here's where some people are going to go wrong. You're going to go ahead and times that by 2. Don't do it. That is the coefficient ratio stuff. You do that next. First of all, you don't times that by 2 now. That's the MR of gold. So let's work out the moles of gold. 0.175 divided by 197, and that gives us 8.88 times 10 to the minus 4. 8.88 times 10 to the minus 4. Way, you've scored some marks, possibly 2. Okay, what next? Next thing, I want to use this ratio. How much chlorine should we make? Well, the ratio, what's the ratio? It's 2 to 3. This is the point where you use these numbers when you're doing the ratio. So I'm going to write, so even if I screw the next bit up, the examiner might give me the mark because I've put the ratio is 2 to 3. So I need to increase this number of moles by 2 to 3. How do we do that? I'm going to times it by 3 over 2. So if you do 8.88 times 10 to the minus 4 times 3 over 2 times 1.5 basically. So times 3 divided by 2. And we are going to get 1.33 times 10 to the minus 3. So 1.332, whatever, there's a load of numbers, times 10 to the minus 3. So it's got bigger. And that's what you'd expect when you're going from 2 to 3. So that's my moles of chlorine. And I'm going to have definitely smashed out another mark for that. Now, what do I need to do next? It wants the mass, it wants it in milligrams. So I'm going to take this N, I'm going to put that up there. What have I got to do to find M? I've got to times it by the MR. Guess what, peeps? We got the MR right there. But don't forget, chlorine is diatomic. It has this too. That means diatomic. So I need to double that to 71. So I'm going to do the MR of chlorine, which is 71. That's the MR. I'm going to times it by the moles, and that is going to give me my mass of chlorine. Let's go ahead and do it. Times 71. My mass of chlorine is 0.0946. So, guys, we have got a mass, running out of room, of 0.0946, and that is grams, guys. What have they asked for the answer to be in? So that gives me my 4th out of 5 marks. What have they asked for the answer to be in? They want it in milligrams. Now that's a smaller unit, and when we go down, you do the opposite of what you think. When you go down, you multiply. So I'm going to times that by 1,000. And if I times by 1,000, you get 94.6. So to convert grams to milligrams, times by 1,000, and you're going to get 94.6. A lot of people are like, but I don't get it. Milligrams are smaller than grams. Why do I have to times by 1,000? Think about your height. You might be 1.5 meters. If you put that into a smaller unit like centimeters, that's 150. The number gets bigger. So when we go from a big unit into a small unit, the number gets bigger. Think about your height, 1.5 meters, put it into centimeters, 150 centimeters. You go into a smaller unit, the number gets bigger. We're dealing in thousands here, folks. Right, let's go, let's go, let's go. There you go. That's going to be your last mark, all 5 marks. Let's move on. Gotta say, this was a tricky paper, and why you must do all of the papers before you hit the exam. This question's about elements. Cesium is in group 1 of the periodic table. 7.1, explain what happens to cesium atoms and to oxygen atoms when cesium reacts with oxygen to produce cesium oxide. You should answer in terms of electrons. Guys, this is a really common question. Cesium, they could use magnesium, they could use sodium, they could use lithium and oxygen, they could use sodium and chlorine. It's basically asking you what happens when an ionic bond forms, and it's worth 4 fat marks. You've got to learn this one. This one has come up maybe 5 times out of 8 years, eight lots of exams. So you've got to learn this one, right? It comes up a lot and it's worth 4 fat marks and they're easy marks. So think about cesium. It's in group 1. Okay, group 1 means when it's an ion, it has a plus charge. Think about oxygen. It's in group 6. Oxygen is in group 6. It needs 2 electrons. It becomes -2. So what has gone on between these bad boys? Well, what's actually happened is cesium, which has 1 electron in the outer shell, bumps into oxygen, which has 6 electrons in its outer shell. Oxygen's unhappy, it wants 2. Cesium wants to get rid of 1. So cesium gives an electron to oxygen. Now, if we just say that, we'll pick up 2 marks. If we say cesium gives an electron to oxygen, you're going to get 2 fat marks, but you're not going to get all 4. Why? Because oxygen is still unhappy. We need to have 2 cesium atoms to make oxygen happy. So each cesium atom gives 1 electron to oxygen, or we say oxygen gains 2 electrons from 2 cesium atoms. So it gets 1 electron from each cesium, something that describes that. And then that's probably going to get you like 3 marks. And then the last mark is to say they are now have full outer shells. They're ions, cesium plus, oxygen 2 minus, blah, 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 blah. You can say they form an ionic bond if you like. Lovely, lovely. I like to overwrite and write some extra things in because sometimes on the mark scheme, that last mark, there's like 4 things you could put. So I like to put it all. So first of all, I'm going to say cesium, I'm going to break it down for you, gives, this is the simplest thing you could say, electrons to oxygen. If you just said cesium loses electrons, you'll get 1 mark. I think that's normally 2 marks because what you're doing here is you're saying cesium gives electrons to oxygen from 2. Now to get the numbers right is the 3rd mark. So 2 cesium atoms give 1, this is a better way of saying it, this would get you 3 marks, electron each to an oxygen atom. I've kind of messed that up. That gets both electrons, but you get the idea. So I'm trying to say oxygen gets 2 electrons and they've come from 2 cesium atoms. That would have been a much better way to say it and it's worth 3 marks if you just say that correctly. Personally, it's better to say oxygen takes 2 electrons, 1 from each cesium atom. Bosh, you're going to get the marks. You need to explain that basically in words for 3 marks. Now, the 4th mark, I'm going to just gamble at about 3 or 4 different points. So I'm going to say both become ions with full outer shells. So they're both happy now. They've got full outer shells. They're both stable. And I want to say cesium +1 ion and oxygen O2 minus ion. So I'm giving you the ionic charges. The exact that could also be on there as well. They form an ionic bond. Attraction between CS plus and O2 minus. Okay, there we go. Lovely, kabubbly. Okay, I said they got full out shells. I said they're ions. I said they're attracted to each other because one's positive, one's negative. Bish, bash, bosh. That's definitely going to get you the other marks. Okay, let's move on. I like to long out these questions, you know. Explain why cesium is more reactive than sodium. You should answer in terms of electrons. This is another one you need to know off by heart, peeps. So if you think about it, cesium's right at the bottom of group 1 and sodium's halfway. So sodium is in period 3, so it has 3 shells. You get the idea, right? The only problem with my drawing here is I've not really left myself. Oh my days. Hold on. Hold on. Bear with me, peeps. I need to give myself some room. There is that. Why do I need to give myself room? Because cesium is further down the group. And what do we know about when you're further down the group? When you're further down the group, you've got even more shells. So cesium is like this. Okay. I'm going to do just like, yeah, I don't know. Okay. I'm getting a bit excited now. Cesium is bigger. So basically, what do we want to say here? We want to say cesium, has more shells. Guess what? Same marking point. You could just say cesium is bigger. That will get you the mark. So lovely. We're off the board. Cesium's bigger. What does that mean? In cesium, the outer electron. Remember, they're group one, so they've only got one electron in the outer shell. The outer electron is further from the nucleus. There's another mark, bosh. Obviously, if it's bigger, the electron's further. Let's draw that little electron on. Bosh, bish, bash. Right, there's the electron in sodium. Look how far it is in cesium from the nucleus. It's a lot further, the distance. And what are these atoms trying to do? So they want to lose an electron. Um, this means it is less attracted to the positive nucleus. Now, you don't have to point that out. I like to point it out, but the nucleus is positive and there's less attraction in the cesium because it's further, it's feeling less attraction. And what we can write here is, therefore, it is easier for cesium to lose the electron. So it's more easily lost. And that's your fourth mark. So you've really explained it, that it's bigger or has more shells. The electron is further, so feels less attraction, so is more easily lost. Now you can also say, bonus mark, cesium has more shielding. And if you just put that, you're going to get a mark, right? The more shells you've got, the more shielding you've got. So that's a nice quick statement. Shielding means that this electron, not only is it further, but there's more walls, more layers in between it and that positive. Imagine that's like a magnet trying to pull that in, but there's barriers in between blocking that pull. So we call that shielding. All right. Whew. Oh my gosh. 7.3. We're right there, peeps. We're at the end. Oh my days. Figure 6 shows part of Mendeleev's periodic table. Figure 6, we've got O, S, Se, selenium, fluorine, chlorine, bromine. Yeah. Explain why the periodic table places iodine before tellurium or tellurium, but then Mendeleev placed tellurium before iodine. Right. So, the reason why early periodic tables put I before TE, we can see why. Look at the numbers, peeps. We'd say, so the first point is early periodic tables. Oh my days, look how I spelled periodic. Periodi. Early periodic tables put I before TE because they were, oh my gosh, they were arranged in order of atomic weight or atomic weight, and I has smaller mass. Okay, so they were arranged by atomic weight or mass. Essentially, I've longed that out. You just needed to say because I has a lower mass. And then we need to say, but why did Mendeleev switch them round? So what Mendeleev did, uh, Mendeleev, can't spell his name even though it's in front of me. Mendeleev arranged by chemical properties as well as mass. Iodine had similar chemical reactions or chemical properties to Br, Cl, and F. So the beauty of what Mendeleev did, right? Mendeleev said, yeah, I'm going to do what everyone else is doing. He said, I'm going to arrange everything by mass like everyone has done before. Check it out. 16, 19, 32, 35, 79, 80. He put 127, 128. Then he said, hey, but I reacts in with water, reacts with whatever, metals, reacts in the same way as these bad boys. I'm swapping them around, guys. I'm not making mass like my number one thing in the world. Mass is not my ruler. I am going to take into account chemical properties. I will still obey the mass rule, but I'm also gonna watch out for the chemical properties, and where I see fit, I'm gonna make swapsies. And that's what he did. The other thing you've got to remember is that he left gaps. It's not tested in this question here, but it often is. So when you're revising Mendeleev, just know that he arranged things by mass in order of mass. However, he took into account chemical properties and he left gaps where need be. Okay, that's the end, guys. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Let's get ready for the exams.
You're still here? It's over.